Welcome to this video that will be used to discuss how we can go about solving trigonometric equations. We will review linear trig equations, and we will then move on to second degree trig equations, which will model the patterns of quadratics. We will look at working in both radians and degrees. And we will look at how to come up with general solutions as well as exact and approximate solutions to describe solutions to quadratic equations. All right, so let's start with what normally would be a review of prerequisite skills, so things that students are able to do before they go into our journey in Pre-Calc 12A. So if I take this equation up here, we have a rule that says if the domain, that's this part here, that's called the domain, if that is given in degrees, then our solutions should be in degrees. If this is provided in radians, well then we would expect our answer to be in radians. I'll just quickly sketch over here this diagram, which we should all be familiar with. And this diagram is for how to get the measure of a rotation angle in degrees if, so for example, if you had a 40-degree reference angle, it's not drawn very well, but if that was a 40-degree angle, well, in quadrant 2, if you had a 40-degree angle in the corner here, this angle would be 140, or 180 minus whatever that little angle is. If down in this corner you had a 40-degree angle, well then your rotation angle starting at standard position would be 180 plus 40, or 220 degrees. Hence the formula 180 plus theta, 180 minus theta. If you had a 40-degree reference angle here, well then your angle would be 360, take away 40, or 360 minus theta if you're in quadrant 1. So these are your quadrant 4. So these are how your quadrants are numbered: 1, 2, 3, and 4. And you're going to determine which quadrants your angle could end up in. And then based upon that, you're going to choose the correct formula here, or notation. And you're going to tell me what those angles could possibly be. All right, so if I go back to this first one, if you don't have a calculator nearby, you should pause the video, run and grab your calculator, because we're going to be relying heavily upon our calculators to do this section. Okay, so I'm going to use what's called a reference angle system. So what we're going to do is find a reference angle, which is this little angle in quadrant 1 that matches up with this particular trig ratio. And then we're going to determine in which quadrants we could find our angle based upon whether your trig ratio is positive or negative. Okay, so we're in degrees, so make sure you have your calculator set to degree mode, which I do here, and I need to find the angle associated with this sine ratio. So you're going to go inverse sine of 0.9659, and that will give us 75 degrees. The sine ratio, as we can tell here, is a positive. Well, the sine ratio, psi, you recall we've talked about, it is the y value over the r value. The y value, then it must be positive, and the y value is only positive in your top 2 quadrants. So you know that this angle could possibly be in quadrant 1 or 2. Well, we have the one in quadrant 1. It's 75 degrees. The problem is your calculator only gives you one angle. You need to know how to find all possibilities. So we have this one over here, which is 75. That's theta. Well, I want the one in quadrant 2 that has a 75-degree angle down here in the corner, because it will also have the same trig ratios as this angle, only difference being it's in quadrant 2, but it will still have a positive sine ratio. So here's your possible answers then. Theta could be in quadrant 1, it's just the reference angle. But if I put that reference angle in quadrant 2, it's 180 subtract the reference angle, or 105 degrees. Now you could check your work here, find the sine of 75. You should get something very close to that. And then find the sine of 105, and you should also get something very close to that. Now imagine that this question had said sine theta equals negative 0.9659. Well, let's just look at how it would be done differently. It would start out the exact same way. We would find a reference angle, and we'd find quadrants. Now, this is the most important thing that students need to understand. When you're finding the reference angle, do not input the negative. No negatives when finding your reference angle. Bar none, the most common mistake students make is they input the negative into their calculator, and then it gives them an angle that is a possible angle, but then they have a hard time finding the other angles. There are other strategies that you can use, and if you understand kind of the trigonometry of everything and of rotation angles, you can figure out a way to do it by putting the negative in there. I do not, so the method I'm showing you relies upon you not putting the negative in when you're finding the reference angle. So if you do it that way, you're going to get the same reference angle. The only thing that will be different is because now sine is negative. Well, sine is only negative where y is negative, which is down in the bottom two quadrants. So now it's 3 and 4 instead of 1 and 2. So you can see here, my answers were 75 and 105 because my angle was in quadrant 1, which is 75, or quadrant 2, which is 180, subtract your reference angle, 105. Well, in this question, we are in quadrant 3 or 4. Well, in quadrant 3, if that was a 75-degree reference angle, it's 180 plus 75. 255 would be one possibility. Or it's 360 subtract 75, which would be 285 degrees. Those would be your two possible angles. So notice the difference. Reference angle didn't change, but the quadrants changed because my trig ratio was negative, and the sine ratio can only be negative in your bottom two quadrants. So therefore, I had to rely upon generating a 75-degree reference angle, and these two formulas allow us to do that in quadrants 3 and 4. Now this is the most important, this is the foundation to make you have the skill set to solve a trigonometric equation. So if you're still a bit puzzled, well, maybe you want to back up the video and just carefully watch this again, and once this all kind of falls into place for you, then you should be set up to have a very easy time following through the rest of this video. All right, so here is another one. This one is now secant. I do notice, though, it's in radians. All right, so if it's in radians, what we're going to do is we're going to switch our calculator to radian mode now. So figure out how to do that on your calculator. Getting my calculator ready here, just one sec. So radians. Okay, sorry about that. I had a new calculator here that I haven't used before, so I just had to figure out the buttons. We're good to go. All right, so I'm going to find my reference angle in radians, and then I'm going to go quadrants. Now remember, to do this on a calculator, there's no inverse secant button. So what you need to do is use inverse cosine. Input your number, no negative, remember, 1.3054. Before you hit equals or enter, you need to hit your reciprocal button, which is either x to the -1, or some calculators, it will be a 1/x button. Then hit enter. Close your bracket if there's brackets there. All right, so I'm going to input that on my calculator. Inverse cosine. 1.3054. Hit my reciprocal button. Again, new calculator, I gotta find the button here. is. And I'm getting 0.698. And secant, remember, is the reciprocal of cos. Cos is x over your r value. So x must be negative because r is always positive. X has to be negative. Well, that tells me that I am over here and here. So we are in quadrants 2 and 3. Now, because we're in radians, our formulas are going to switch and be theta will still be our quadrant 1 version. Now, this question, we're not in quadrant 1, so that's not going to be an answer. But instead of 180, we now switch to pi subtract theta, 180 or pi radians plus theta. And then instead of 360, it's now 2 pi minus theta. So our formulas have just changed to reflect that we're working in radians. All right, so let's get our possible answers then. So theta could be pi subtract this angle. So pi subtract 0.698 is 2.444. That's quadrant 2. And then in quadrant 3, it's pi plus the reference angle. So pi plus 0.698. And I get 3.840 if I round it off. 3.840. Now, one thing I forgot to do, let me back up a second. Oh yeah, sorry. When I got to here, I forgot to look back up at this. We have to always make sure that I've only given you the answers from 0. I did one term basically, 0 in this one to 360. Right, so that would be within one term, 0 to 360. However, if I look at this, it's saying that I can give answers from negative 360 all the way up to 720. So what we need to make sure we do is give all the possible answers. Well, to get angles, so we got, I'll just highlight them. We had this one, and we had this one. So this one was 75, and this one was 105. Well, what I need are all the possible angles between negative 360 and 720 that are in the exact same location as these. Those are called coterminal angles. Well, we've gone over how to do that. How do we find more angles in the same place as these ones? We use the strategy of adding or subtracting 360. That'll give you more angles that are in the exact same place. So we're going to take each of these angles. So let's take 255, and we're going to add 360. And that's going to give me 615. So there's another answer. I'm going to take 285, and I'm also going to add 360. That'll give me 645. There's another answer. 45. Sorry. That's a bad 6, but that's a 6. Now, if I added 360 to either of those, they would be larger than 720. So I know there's no more positive angles in the same place. So I'm going to go back to these two, and now I'm going to subtract 360. So 255, and I take away 360, I get negative 105. And then 285, subtract 360, would be a negative 75. So we actually ended up with 1, 2, 3, 4, 5, 6 possible answers. So we have to check that our domain, that we give all the possible answers in our domain, not just the ones between 0 and 360. Sorry that I overlooked that in the beginning. Okay, so let's go back to this now that I've remembered that extra final step for these. Now negative 2 pi up to 2 pi. So remember 2 pi is roughly 6.28, which means one full circle. And then this is negative 6.28, right? 3.14 doubled. These were the two angles we got when we did one full turn. So that would be 0 to 2 pi. So there's no more positive answers then. Well, now I need to get the negative ones in the same place as the two that I just found. So I found one over here and one over here. So to get another angle in the same place as each of these, now I can't get any more positive ones because they'd be too large, but I could take away, now not 360 because we're in degrees this time, so take away 2 pi. So 2.444 subtract 2 pi, negative 3.839, actually negative 3.840 and that. And if you go 3.840 and subtract 2 pi, you get negative 2.444. This is the only ratio, well, secant and cosine is the only trig ratio where the positive angles turn out to be the exact same negative angles. That does not happen for sine, sine or tangent or their reciprocals, but it does work for secant and cosine. All right. Oops. Now, sometimes you may have to do a little bit of extra work with this is still linear because your trig ratio is to the first, but it's not isolated like it was in the first two. So you just have to do a little bit of rearranging first. So all I'm going to have to do here is go cos theta, take your plus 1 to the other side, get negative 1, still have your radical 2 in front, then divide both sides by radical 2, and you're down to cosine theta is negative 1 over square root 2. All right, so we're going to go reference angle, figure out what the reference angle is, Q for quadrants. Well, with all the work we've been doing lately with special angles, I hope this one looks familiar and you say, hey, wait a second, that's one of my special angles. And it actually is the cosine of 45 degrees. Now, if you didn't realize that, you could still find it on your calculator. However, hopefully that one, again, you've done enough diagrams over the last little while to realize that is a special angle. Cosine can be negative over here and here, like the last one. So we're in quadrants 2 and 3. So remember, in quadrant 2, it's 180 subtract the reference angle. And down here, to get your rotation angle, it's 180 plus the reference angle. And in this case, the reference angle is 45. So here are 2 possible solutions to get us started. So I'll look here and see that I can make actually 2 positive rotations and 1 negative rotation. So I'm going to get 180 minus 45, 135, 180 plus 45, 225. Because I'm allowed to go to 720, I'm going to now get 2 more angles in the same place as these 2 by adding 360. So 135 plus 360 is 495. I'm going to add 360 to 225. That'll give me 585. Now, of course, you couldn't add 360 to these again because it would be beyond 720. However, I could go back to these and subtract 360 from each one. 135 minus 360 is a negative 225, and 225 minus 360 is a negative 135. As I mentioned in the last one, with cosine or secant, you get the same negative angles as you do positive. You'll learn why that happens in our next unit, but for now, if you pick up on that, it can save you a little bit of time and not have to actually do the subtraction. There you have it. You've solved a linear trig equation. That one was in degrees. Well, the other so those first 3 have all involved angles that were somewhere within quadrants 1, 2, 3, or 4. You also have to be able to deal with angles that end up right on a quadrant boundary, the ones we call quadrantals. So they're not actually in a quadrant because they're right on an axis. And we've worked with how to do this using what's called the unit circle. So remember the unit circle. You have your ordered pairs. If you're over here, you're over 1 and up 0. If you're up here, you've gone left or right 0, but you moved up 1. And if you're here, you've gone left 1 unit, and you have not moved up or down. And then if you were down here, you've not gone left or right, but you are sitting at position negative 1. And then there's a circle with a radius of 1 that passes through each of these points. So R is 1. And then we know our trig ratios, we hope. Our cos theta is x over r. Sine of theta is the y over the r. And the tangent of theta is the y divided by the x. Okay, so if we know all of that, we'll go over here, and we're going to use this system when your trig ratio, so in this case, notice the difference here, so sine x is -1. Now it wants it in radians, because I see these are given in radians. We need to draw the distinction that sine is referring to the y value. Remember, r is always 1, so the sine ratio in this case is -1, is telling me that the y value is -1. Well, if you look on the unit circle, there is only one spot where the y value is -1. So it's not a reference angle system, so please don't write down, when you see here it's 1, a -1, or 0, it needs to use the unit circle method, or strategy I guess we'll call it, not a reference angle strategy. And you say, all right, well, this is the only place down here where the y value is -1. So you say, okay, well, what angle is that? That angle in radians is 3 pi over 2. Now, I'm allowed to get another angle in the same place as that, so I can add 2 pi to this. Now, I'm going to So if you're in radians and you're trying to get multiple angles in the same place, you got to be able to work a little bit with fractions. So you just have to say, well, if it's over 2 and I'm adding 2 pi over 1, that's really the same thing as 3 pi over 2 plus 4 pi over 2. I just want the denominators to be the same. So that would give me 7 pi over 2. So there's another possible angle. Now, if you're putting this over 2, it would be 8 pi over 2. That's the same as 4 pi, so I couldn't add another 2 pi to that because it would be bigger than that one. Well, like before, we're allowed to subtract 2 pi. So instead of 3 pi over 2 plus 4 pi over 2, you're just going to take away 4 pi over 2, which would give you the angle negative pi over 2, which we can clearly see that if I started here and rotated negative pi over 2, I would end up right in the same spot. So I get these 3 possible angles. So these are how we deal with what are called quadrantal angles. Angles that fall right on one of your axes, either the x or the y axis, so they're not situated within a quadrant. All right, so now let's take a look at a couple more. So this one, you'll see here, it's still linear because your trig ratios are to the first. We're building towards solving trig equations where these are going to have squareds on them. But we have to have linears kind of mastered before we move on to that. So if I take A, the first thing I'm going to want to do is isolate my trig ratio by itself. And I say, yeah, but there's 2 of them. Well, trig ratios are like variables. You can collect them. So I've got 3 cos theta. I'm going to move this cos theta over here, minus cos theta. I'm going to take this one, and I'm going to add 1 by, add 1, take that 1 the other way. Now I've got 3 cos theta minus 1 cos theta. Think of it like 3m minus 1m. You collect them. Well, instead of m's, they're cos thetas. This would be 2 cos theta equals 2. Divide both sides by 2. Cosine of theta must equal 1. Now, as soon as you see the sine or the cosine, this is not true for tan, but sine or cosine equal to 1, -1, or 0, you should immediately be thinking unit circle system. Cos, I need to know my trig ratios. Cos is the x over the r always being positive, so this is saying that the x must equal 1. That's the only spot where x equals 1. We are in, what are we in here? We're in radians, and we're allowed -2 pi to 2 pi. Well, this would, is there equal sign? Yes, there is an equal sign, so I can't equal 2 pi. Here's the reason I was saying that. These x's? Yeah, they're theta. So theta could be 0 in radians, or it could be, if I did a full turn, 2 pi. Going the other way, it could also be -2 pi. There's your three possible answers. Okay, let's look at B. B is working in degrees. Again, isolate your trig ratio. 4 secant x. I'll take the 8 to the other side. I'm going to divide both sides by 4. Secant of x would equal -2, -8 over 4. Now, if you'd rather work with cosine, you could just flip that, or, now this is not your quadrantal system, this is now reference angle system. So I'm going to go reference angle and quadrants. Make sure you switch your calculator back to degrees. So I'm going to go 3. All right, so I need to go inverse cosine of, remember, no negative, so I'm just putting in the number 2, but I'm going to take its reciprocal, which is 1/2, but I'll just hit the reciprocal button and it'll do it for me. And it spits out 60 degrees. And secant, which is cosine, is only negative over here and here, because that's where x is negative. So we're in quadrants 2 and 3, meaning x could be, so they're using x as their angle. So x could be 180 minus 60, which is 120. That's your quadrant 2 angle. And then if your reference, if this little angle was 60 and you wanted to get your angle down in quadrant 3, it's 180 plus 60, which would be 240 degrees. Now this one, the domain was restricted to just 0 to 360, so one positive rotation. So these are the only two angles you're going to get. There's your answers, 120 and 240. All right, so now hopefully you have a grasp of what we've been discussing, and we're going to move on to solving quadratic trigonometric equations. The good news is essentially it's the exact same thing, except we will turn quadratics into two linears. For example, we've already done a unit on quadratics. Suppose you had this quadratic from back in our unit on quadratics and you wanted to solve. Well, if we try to factor them first, this one will factor. It's a hard trinomial, so I need two numbers that multiply to give -2 and add to give a +1. Well, those numbers would be 2x plus 2 and 2x subtract 1, giving me, and then this one, sorry, divides by 2. So this first factor would be x plus 1, and my second factor would be 2x subtract 1, giving me answers of -1 or +1/2. So that's a review of solving a quadratic by factoring. Now, if it didn't factor, you could perhaps have to maybe use the quadratic formula if necessary, which may happen in some of these questions. And then from your quadratic formula, you'll get your two possible answers. Well, if you look at this, 2 sine squared x plus sine x equals 1, you say, well, that's a trig equation, but now it's got a squared on it. So it's a quadratic trigonometric equation. All the ones we've done so far have been linear trig equations because all the trig ratios were to the first power. If you look at the pattern of this, do you see a parallel to the pattern of this? Basically, all that's happened is the letter x has been replaced by sine of x, sine of x. What many students like to do is a substitution. They introduced a new variable. Now don't use x because it's already taken. So m is a common choice. Let's let m equal sine of x. If you do that, the equation is going to, so sine, if you've never seen this before, sine squared x means sine of x in brackets squared. So this really means sine of x squared. So it's, if m is sine of x, this is 2m squared plus m equals 1, which is now identical to this equation, except the x's have been interchanged for m's. So you do the same steps. I'm not going to show them again. and you'd get m equals -1 and m equals 1/2. Then you resubstitute, so you switch back from m's to what m is actually taking the place of. So the m was there to take the place of sine x. So this now becomes sine x is equal to -1 and sine x is equal to 1/2. Now what I like about this equation is that it's going to force us to use both methods. Now if we just retrace our steps for a second, here's all that happens with quadratic trig equations. They turn out to be two linears at the end. So as you can see, there's nothing new other than how to start from your quadratic and turn it into your two linears. So now I've got two linear trig equations like we've been solving before we got to this slide. And sine is -1 only on the unit circle. So this is your quadrantal strategy. Psi, remember, goes with y. Y is -1 down here. So now I need to say, well, what angles could this be? Well, what's their domain? So 0 to 4 pi. So 4 pi means 2 positive rotations. It's in radians, so it wants angles in radians. This angle in radians, positive, would be 3 pi over 2, which is equivalent to 270. And then you could add 2 pi, so 2 pi would be 4 pi over 2 to 3 pi over 2. That's 7 pi over 2. Those would be the only angles from that one. If it's not 1 or -1 or 0, then you go to your reference angle system. So I'm going to go reference angle and Q for quadrants. Quadrants here, psi is y, and notice it's positive. Well, sine is only positive up here and here, so we're in quadrants 1 or 2. Having a sine of 1/2, it is a special angle, so you could do it off your triangle, or you can use your calculator because you are allowed calculators, but I'll just draw this diagram out just to have it. So this is 60, 30, I know it's degrees, we'll switch to radians in a second. That's 2, 1, and that's radical 3. So the diagram here shows us that the angle that has a sine ratio of 1/2 is 30. Well, in radians, that is pi over 6. Okay. Therefore, our angles are going to be theta, which is your reference angle, and then pi minus theta in quadrant 2. That'll give you a rotation angle in this quadrant that has a reference angle of pi over 6 down in the corner. Here are the possible angles we'll come up with then. So pi over 6, because it's in quadrant 1. So that's your reference angle. Now pi minus pi over 6. So this is 1 pi. Just in your head then think 6 over 6. That's the same as 1. So it's 6 pi over 6 minus a pi over 6. That would be 5 pi over 6. You're allowed to get two more positive angles, because you're allowed to make 2 rotations. It was 0 to 4 pi. Now you have to take pi over 6 and add 2 pi. Well, 2 pi, right? If you add 2 pi, that's over 1. But if you're working with fractions, so if it's over 6, this is going to go to 12 pi over 6. So you're going to add 12 pi over 6 to each one of these. So 13 pi over 6, and then if you add 12 to that one, that'll give you 17 pi over 6. So you get these 4 and then these 2. So you have all these angles that would that do work if you substitute them in here in the place of that x. You just switch your calculator to radians if you want it. Pick any one of these 6 angles. Fill them in where the x is, type that statement in your calculator, and it should work if you've input it properly into your calculator. All right, so that's a look at how do you do a quadratic. Now we'll do a couple more. Let's just have a look. Oops. Okay, so let's look at this one. It's in radians again. The first thing I don't like about this one is I don't like dealing with equations with fractions. So I'm just going to double everything. So it's 2 cos squared theta minus cosine of theta equals 0. You can switch out your variable if you like. You don't have to do this step. If you're comfortable working with cos thetas and realizing they're the same thing as having an m or an x there. I'll just do the substitution. I find many students prefer this step. So now it's 2m squared subtract m equals 0. The only way I can solve this in terms of factoring would be with a GCF. Take out m. 2m subtract 1 is equal to 0, giving me two possible answers, 0 or a half. So remember, now we resubstitute. Let's get back to, instead of m is taking the place of cos theta. Cosine theta could be 0. Cosine theta could be 1/2. All right, so now I'm just going to take, as soon as I see 0 here for cos, I know it's unit circle. Cos is x. X is 0 in two spots. It could be up here, or it could also be down here this time. It's the first time we've had multiple locations for a quadrangle. Well, based on, what's my domain? So negative 2 pi to 4 pi. If I start here and go in the positive direction, this angle would be pi over 2. There's one possibility. This angle would be 3 pi over 2. Now we're allowed up to 4 pi, which means 2 turns. So I'm going to add 2 pi to each of these. 2 pi, if your denominator is 2, is the same as 4 over 2. So 4 over 2, add 1 over 2. That's 5 pi over 2. Add 4 over 2 to 3 over 2, you're going to get 7 pi over 2. And then, of course, you could also subtract 2 pi, because it said up here we could go to negative 2 pi. So if I take away 4 pi over 2 from this one, I'll get negative 3 pi over 2. And then subtract 4 pi over 2 from this one, I'll get negative pi over 2. Shouldn't be surprised. The negative version is the same as the positive version, because we're working with cosine. Okay, the other one is reference angle system. So reference angle and quadrants. Now, you got two options here. You can work in special angles, or if you want to get the decimal versions, you can just switch your calculator. Now, what I mean by that is, because this is a special angle, I know that it comes off of this triangle, my 60-30 triangle. 60-30, so 1, 2, square root 3. Cosine of a half, it's got to be 60 degrees, so I could put in here pi over 3 as my reference angle by looking at my triangle. And then cosine can only be positive where x is positive, which would be over here and here, so I know I'm in quadrant 1 or 4. However, if you didn't recognize it as a special angle and you didn't draw the triangle, you could get the decimal equivalent of this by just on your calculator, make sure you're in radians. So radians. And go inverse cosine of a half. And it will give you the decimal equivalent of pi over 3, which is 1.047. So that's if you just do it on a calculator. It makes no difference which one you use. So let's suppose I'll just show you how I could work off of this method. I've shown you how to do it with the fractions already. So let's suppose I was using this version. So then theta could be, in quadrant 1, it's 1.047. Remembering this one down here is in radians, 2 pi, subtract the reference angle. So 2 pi, take away that number. 2 pi, subtract, will give me 5.236. And now I just need to get all the possible angles that are sitting in the same location as these. So I'm going to plus and minus 2 pi. So we're allowed 2 full positive rotations. So I'm going to add 2 pi to each of these. Plus 2. So if I add 2 pi to this one, I get 11.519. Now if I add 2 pi to this one, I get 7.330. And then I'm allowed to go to negative 2 pi, which means I'm allowed 2 negative angles in the same place as these. So now it's 1.047. Subtract 2 pi. Now we shouldn't be surprised because it's cos. We're going to get the negative of that. Negative 5.236. And then we'll get the negative of that, negative 1.047. So another way that people or students will write this is instead of writing these out, and especially if you notice that it's cosine, they won't put these down. Again, what they do is just use this mathematical symbol, plus or minus. That means that one, the positive version and the negative version, plus or minus. Now I couldn't go plus or minus these because they would be 2 negative rotations away, and you're only allowed to make 1 negative rotation. So this one's got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 answers to that quadratic trig equation. The only other thing I want to look at is yes, the last thing I want to look at is how do we get what they'll sometimes ask for are the general solutions. So I haven't given you any specific domain here, other than I said theta could be any real number. That means positives or negatives in both directions and forever. Well, obviously we can't write those all out. So what we have to do is we just solve them the same way. So this is quadratic. Let's set it equal to 0. 3 cos squared of theta minus the cosine of theta, subtract 2, is equal to 0. I'll show you how you, if you don't want to do a substitution, you don't have to. So I'm just going to treat cos theta like an m. Now if you would be more comfortable with an m there and 3m squared minus m minus 2, that's fine. You go ahead. I'll just show you how you can do it without making the substitution. Multiply to get negative 6 and add to get minus 1 would be minus 3 and a plus 2. So it's 3 cos squared theta. So usually that's 3m squared. Sorry, not 3m squared. 3 just cos. 3 cos theta, it's usually 3m, minus, and then 3 cos theta equals 0. So we said the numbers would be minus 3 and plus 2. Divide this one by 3. So we're down to cosine of theta minus 1 and 3 cos theta plus 2 equals 0, giving me cos theta equals 1 or cos theta equals negative 2/3. This is a unit circle, quadrantal angles, and this one would be a reference angle system. So good practice for both. Cos goes with x. X is only 1 right here. So I know that we are talking about, let's suppose, I'll show you both. Let's say it was degrees first, and then we'll do it in radians after that. It's quite simple. Doesn't matter which one, to be honest with you, here when you see it in a second. Okay, so theta could be 0 if we're in degrees, or it could be 360 degrees, or then you could just keep adding or subtracting 360. Well, in fact, if I just worked off of 0 only, that would be enough, because this is all you do in degrees. You write out your first angle that you find, and then you just put here plus 360k, where k could be any element of the integers. Integers meaning positives or negatives, but they can't include decimals. So this means you're going to put here like 1, 2, 3, 4, 5, negative 1, negative 2, negative 3, negative 4, which all that's going to do is add or subtract multiples of 360 to your angle, which is how we find angles that are coterminal. That would be the general solution. Well, this would be in degrees. Well, this one would be really easy in radians, because 0 degrees is also 0 radians. So I'd go 0 radians. Here would be the only difference. It would be 2 pi times k. A lot of times they'll put the k in here, 2k pi. And same thing. K is an element of the integers. So all that happened is 360 got converted to 2 pi. Let's go to the other one, which is, this is a reference angle type question. Quadrants, cosine can only be negative here or here, so we know we're in quadrants 2 and 3. Our reference angle, so I have to go inverse cosine. Remember, no negative when you find the reference angle. And what am I in here? Radians or degrees? I am in, can't see, let's go, shift, set up. So I'm going to do it in degrees first. Shift cosine of 2/3 is 48 degrees, roughly. That's not an answer, though, because that's the quadrant 1 version. I want 48 as a reference angle, but in quadrant 2. So my angle, one possibility could be 180 minus 48, which is 132. Then to get all the possible angles in the same place as 132, you just put plus 360k, where k could be any element of the integer. So that just means you're going to add or subtract multiples of 360. And then theta could also be in quadrant 3. So I just did 2. In quadrant 3, it's 180 plus the reference angle, 228 plus 360k, where k could be any element of the integers. Now if I switch to radians, so that's degrees, this is the radian version of it. So radians, theta would be, here's the only thing you got to do different. Find your angle, your reference angle, in radians. So you got to switch your calculator back to radians. And if I'm in radians, I get 0.841 as my angle. And then my angles, so in quadrant 2, remember it's going to be pi minus the reference angle. In quadrant 3, it's going to be pi plus the reference angle, this being the reference angle. So if I go pi and I subtract 0.841, I get 2.301 plus, and again, instead of 360, you just go with 2 pi times k, where k could be any integer. And then the quadrant 3 version is pi plus that number, 0.841, 3.983. And again, plus 2 pi k, and that would just give you all the possible angles if you just kept adding 2 pi radians, which is full circles, put you right back in those. All right, so that is how you find what they will sometimes call the general solutions for trig equations. So we did both degrees and radians. One thing I will mention is that there are some situations, so for example, let's say I said, I'll just deal with a linear, cos theta is 3/2, and 0 degrees is less than or equal to theta is less than or equal to 360 degrees. So instinctively, a lot of times students go reference angle, and then they go Q for quadrants, and they take their calculator out and they go inverse cosine of 3/2, and all of a sudden they're getting error. And they think they're doing something wrong. And they're doing absolutely nothing wrong. I want you to think about cosine. Right back to your very basic trigonometric identities. Cosine of theta is the adjacent over the hypotenuse. Well, by definition, the hypotenuse has to be bigger than the adjacent, because hypotenuse is the longest side in your diagram. Well, if the bigger number's on the bottom, there's no way that you could take and have this set up so that it's in this fraction, which is having the bigger number on the top and the smaller number on the bottom. So this is an impossible trig ratio. So if it says error, it usually means that you just have a ratio that's not possible, which means there are no possible solutions. And this can happen. And of course, then the converse of that is if I had cosecant of theta is 0.7539, and you start trying to find this on your calculator, same thing, it's not going to work because cosecant is supposed to be, of an angle, is supposed to be the hypotenuse over the opposite. And this one should be bigger than this one, which means when you divide this out, you should be getting something more than 1. This is impossible. Which means it would have no solutions. So you can have trigonometric situations where there are no possible solutions, no angles that would satisfy those conditions. All right, that is a run through on how to solve linear trig equations, and then leading up to that or following that, we progressed into solving trigonometric equations, and we worked both in radians and degrees. So now you should attempt some of our practice problems and get yourself prepared to do a formative assessment on trigonometric equations. Thanks for watching. Best of luck. As always, reach out if you have any questions or concerns.